and I hope this is the first of many meetings of this sort. So here's a plan for today. I'm going to start with some introduction and motivations from QCD. Then I'm going to give some review, very fast review of the holographic model I'm going to be using. Then I'm going to discuss how to include a pion mass in this context, only because it's it's slightly more involved than in other holographic models. You'll see why. And then I'm going to discuss the main part of the results, which is about baryons in this context and holographic realization of quarkyonic matter. And then I will conclude. So let's first review about what we know about the QCD phase diagram. So the QCD phase diagram, if we were to make a very naive guess, would be based on these two things we know about it. The first is that we never see free quarks around us. And the idea is that at low energy, we should only see these bound states, mesons or nucleons. While at high energies, that's at high temperatures or high densities or chemical potentials like here, we know that there is asymptotic freedom in QCD, and so we should see a model of weakly interacting quarks and gluons. And this may seem a very naive idea for a phase diagram, but if you had this idea 45 years ago, you would now have a paper with 600 citations, probably, and this is the original phase diagram. But of course, we know that things are much more complicated than that. And this is this is from 5 years ago now, but this is a rough idea of the phase diagram we think that QCD has, at least in the chiral limits, and we see that it's much more complicated. I don't know, can you see my mouse if I move it?
Yes.
Okay, great.
That's good.
So we know that at high temperatures we have a quark-gluon plasma, then we have the vacuum, let's say the vacuum phase close to the origin, then we have a nuclear matter onset, then we have some different types of transitions. And then we have more exotic possibilities. Quarkyonic matter is the one I'm going to be talking about, maybe some color superconductors and so on. And the problem, even though people are thinking about this, have been thinking about this for 45 years, we don't know much about it. And the reason is that it's not easy to probe this theory in all this phase space. We know things, relative things in some regimes. For example, in the temperature at mu equals 0, so at chemical potential equals 0, you can think about it at low density. We have lattice QTD techniques. We have data from the particles accelerators in this regime. We have data from effective models and phenometrical models near the vacuum phase. And a bit more recently, we have information about this part, which is the cold dense parts, and which is the part I'm going to be focusing about from neutron star information. So why is it interesting? I really don't have to convince you, I think, why QCD is interesting. Everybody agrees on that. It's important for a wide range of phenomena around us, heavy ions, early cosmology, compact stars, etc. But one thing I wanted to highlight is that the recent gravitational wave measurements have, in some sense, transformed neutron stars into our own cold and dense QTD matter laboratories, and even with the temperature of the mergers, not so cold. And so it's a nice time to be thinking about this, about cold and dense matter QCD. And why is it so difficult? It's very difficult because there are perturbative methods that are only useful at high temperatures or high chemical potentials. As I said, lattice works only at mu equals 0 because of the sign problem. There are no exact order parameters except for the superconducting phases around. The phase structure of the system really depends on a lot of the parameters, on the masses of the quarks, on the number of cores or flavors, on where you have a magnetic field or where you have isospin asymmetry, etc. And one of the main reasons why it's difficult is that it's very difficult to construct a model that can describe quarks, mesons, and baryons and compare their free energies of different configurations at the same time. So what is quarkyonic matter in this context, which is my main focus of interest in this talk? Quarkyonic matter, so if you look at the cold dense regime, which is where the region I was pointing out, the region that's interesting for neutron stars, quark and baryonic phases are not really easy to distinguish. There are no really order parameters or many physical ways to distinguish them in this when you're talking about very dense matter. So the question is there something between the asymptotic quarks that we know and the baryons that appear at the onset of nuclear matter? And the first proposal was argued by, or one nice proposal was argued by McLaren and Pisarsky in 2007 and subsequent papers. They called it quarkyonic matter because, as I said, it combines baryonic and quark properties. It was first argued to exist at large n based on power counting on powers of n. So the idea is that for cold and dense matter, you can show that either by counting quark degrees of freedom or by just looking at baryon interactions, you will always have a pressure that scales like NC. And this is different from the vacuum or hadronic phase, where you have a pressure that scales like 1 because of confinement, and the quark-gluon plasma, where you have a pressure that scales like NC squared because of the counting of the gluon degrees of freedom. So the idea, if I focus on the horizontal axis in my diagram, I know that there is some point where there's an onset of baryons. But when I start including interactions, I start having more and more contribution of these sorts here, the pressure scaling like NC, which is the same I have from the asymptotic regime at high density. And so the question is, do I call this quarkyonic? Is it quarks and baryons is both at the same time? And the various question is, are these both two descriptions of the same thing? Are there transitions in between? Is there a quark-hadron continuity? What happens with chiral restoration? What about, and especially what happens when you don't have large n? So the first, it's easy to say what quarkyonic matter is not than what it is. So it's not a phase with two independent gases of baryons coexisting in the same space, and it's also not a mixed phase where you have baryons where the system is in a baryonic phase in some region of space and in a quark phase in some other region. It's neither of those things. And a nice idea was proposed a couple of years ago, very recently, by McLaren and Reddy, and they argue that it's better to think about this in momentum space, and they argue that this phase should have a structure that's a layered structure in momentum space, in which you start from a Fermi sphere of baryons, and then at some point you have a Fermi sphere of quarks growing inside of it, and a Fermi shell of baryons on top of it, and at some point the Fermi shell of baryons disappears, and you're left with a Fermi sphere of quarks. So this thing in the middle is supposed to be what you're talking about when you have quarkyonic matter. And the physical consequences of this picture in the middle is that low energy excitations or transport properties are near the surface here, and they are dominated by baryon physics. But bulk properties such as the pressure also have contributions from all the states here, and in particular they also have contributions from quarks. So I will choose to work to try to answer some of these questions using holography for different reasons. The first one is that it allows me to disentangle in some way the physics of confinement and chiral symmetry breaking. It also allows me to make contact with NJL morphometrical models like NJL and not only QCD. It will allow me to construct an effective model, which is really a theory which has quarks, mesons, and baryons on the same.
Can I make a question, a very simple one? I'm sorry.
Yeah, sure.
Just understand the nomenclature. What do you mean with quark matter? You mean exactly the same of quark matter we expect to have inside quark stars, something like that?
I just mean in this regime, I just mean a dense quark-gluon plasma.
Ah, okay. So high enough temperature. So quark-gluon plasma.
No, I mean it could.
Quarks like a quark star or something.
There could also be quark matter in the core of neutron stars, not in the what you generally think about.
Yes, but in that case, you have less than 10 to the 12 Kelvin. So this is not the quark-gluon plasma. That's why I mean. What kind of?
I mean phases where you can think of the basic degrees of freedom as quarks, not only quark-gluon plasma, also
okay.
this regime.
Also this matter, okay.
Yeah.
Thank you.
You're welcome. Yeah, please interrupt me for questions. And as always, with holography, it also allows me to get a geometrical intuition about some QFT phenomena from the bulk. And the goal is to search for description of quarkyonic matter in the dense core regime from holography, to study the effect of the pion mass, and I'll show you why this is interesting in this context, and to find maybe hints about new critical points in the phase diagram and hints about whether quark Hadron continuity might exist or not. So if there are no more questions now, then maybe I can start with a very quick review of the Witten-Sakai-Sugimoto model. So this is a brain construction of the following type. I have D4 brains on these directions here. This is in type 2A. The NC D4 brains are the background geometry, generate the background geometry and the gluon physics, and in particular Hawking page type transition, which is generally associated to confinement and confinement in the field theory. There is an X4 circle which is compactified with boundary conditions such that there is no supersymmetry left. There are NF pairs of D8 and anti-D8 brains which represent the left and right flavors of the matter physics. And there are three parameters in the model, which are lambda, MKK, which is the Kaluza-Klein scale of the X4 circle, and L, which is the asymptotic separation of the D8s and the anti-D8s. And it has been successfully used to compute many properties of group balls, mesons, and baryons, which are in the right ballpark of what we know from experiments. So focusing on the regime where here I have a black hole for concreteness. There are three types of solutions that one gets from the action, which is a combination of the DBI action, so the action for the D8 brains, which is a combination of the DBI action plus possible sources. And there are three types of solutions here. One is the so-called mesonic solution on the left, where the brains join in the bulk, and when they join, this is a geometric realization of chiral symmetry breaking, because the asymptotic gauge fields I have on both brains become only one set of gauge fields in the interior. This is mesonic and there's no quark density. Then there is the so-called quark or quark-gluon plasma solution, which is chirally restored and where the brains are straight. And then there are possible baryonic solutions where I have some other sources related with baryons, which I will discuss in more detail later. And the basic idea of the phase diagram I get is that this is the Hawking page transition of the background I was telling you about. This is the mesonic phase, which is chiral broken, and this is the quark phase here. And this is all the time I will be speaking about the phase diagram in temperature and baryon chemical potential here. And one nice thing about yeah.
You are putting your CFT on a sphere in that case if you are talking about the transition, or what's the topology of the base manifold? So the
idea is that you have always two directions which have the topology of a cigar, and depending on which side of the Hawking page transition you are, those are either X4 and either U and the time circle, or either U and the X4 circle. Okay, in one case you have a black 4, and in the other case you have the cigar shape here. So this is the X4 direction, and this is the holographic direction. Okay, and by moving one of the parameters I said I had in this model, which is L, again the asymptotic separation of the brains, I can change the location of this Hawking page transition. And I will choose, for reasons that will become clear afterwards, I will choose to work in a limits where this distance is small, and which I think about this transition here as being at very low temperatures. And this is good in some senses and bad in some others. It's good because it allows me to get closer, and it's what's shown in this paper here, to some models like NJL. It's bad because it makes me lose some top-down control about what's happening. And it's, again, good because it gives me a richer phase structure of the model. I have a better understanding. I have the possibility of having chiral restoration at infinity, and some other phenomena like inverse magnetic catalysis, hints of quark continuity, and so on. in different papers in the literature. And I want to point out that in this limit, if you take this line here down, then this diagram, this phase diagram, without any baryons, without considering any baryons, is exactly similar to what our naive first guess we had for the QCD phase diagram. So in that sense, it's kind of nice. And most of what I'm going to talk about is going to be in this geometry. It would be nice, and it's not easy to generalize it to the general to the whole thing. So the question is, how does the presence of the quark mass or the baryons affect this model? And for the baryons, for the pion mass or the quark mass, normally in a brane model, what you would do is you would simply separate a bit in a transversal direction the flavor branes and the color branes, and that would give a mass to the, in this case, to the D4, D8 strings, and that would be the same as giving a mass to the fundamental quarks. But the problem is that in the Sakai-Sugimoto model, you cannot do that. And you cannot do that because simply these are D8 branes, and there are no more directions to move them to get this space. So you have to do it in some effective way. And this has never been done. This had never been done at the level of the phase diagram. So what we do is we follow a suggestion in a paper by Arani and Kutasov, and where they propose to perturb the action by an extra term like this, which is proportional to the quark mass you want to include, and which connects the left and the right quarks, and you need to connect them with a Wilson line in between them, because they live in different branes on the horizon. And when you include this in the action, you can see that it passes some non-trivial checks. It gives, of course, an explicit chiral symmetry breaking. The VEV of this operator is related to the quark, to the chiral condensate. And when you go to the limit in which famously the Sakai-Sugimoto model becomes the chiral Lagrangian, it gives exactly the usual pion mass term for that in chiral perturbation theory. However, at strong coupling, I have the supergravity description, and the nice thing is that in this limit, the VEV of this operator is dominated by the Wilson line in the middle. And the way to compute this VEV is basically, as always with Wilson lines and Wilson loops, to compute a minimal area. And so what it does is you are adding to the system a cost in how much area there is in between these branes. So in this colored region here, and this is the Wilson line. And what this, let's say, worksheet instanton does is it gives an extra tension which pulls the branes, the flavor branes upwards in the holographic direction. So at the level of the Mesonic solution, that's all it does. It just changes a bit the embedding, but that's it. But it's interesting what it does at the level of the solutions which have quark charges. And what it does is that it deforms a bit the solution that has straight branes. The solution with straight branes now is not a solution of the equations anymore. So it's deformed, and it's deformed in such a way that in the very low and very close to the horizon here, these branes touch the horizon, but they touch each other also. So you have no more explicitly chirally restored solutions. And moreover, in some regimes, there's an extra phase that appears, an extra configuration that becomes stable in some regime, which we call low temperature quark here. That's what LTQ stands for, which you can also refer it as string solution. And the idea is that this extra tension from the worksheet instanton pulls some of the quark charges that were hidden below the horizon. It pulls them out in the form of fundamental strings. So you have now these three types of solutions, and these two types are really continuously connected to each other, and they are really two regimes of the same solution. And when you look at how it changes the phase diagram, it changes it a bit when you have very low masses, but when you increase just a bit the mass and increase it above the physical value, let's say for some value of the parameters, then you get an interesting effect, and you get the effect that it can really break this quarter line, this quarter circle line of first order phase transition we had in the model, and it breaks it And it allows you to connect continuously all the phases in the model in this way. So you can go from mesonic to the low temperature quark to the high temperature quark solution without ever jumping. And that's very nice, and that's the type of thing you expect when you include the pion mass. And moreover, it's very similar to what has appeared last year in a recent paper, which don't ask me how they do it, but they managed to overcome the sign problem in the limit of heavy quarks. So in the limit of heavy quarks, under some approximations, they managed to study how the phase diagram of the theory looks like, and they get a phase diagram that looks like this.
This is just a curiosity. This is just a crossover, or is a higher order phase transition? What do you mean by
this one is a crossover, and this one is a second order. And it's second order because I think this is not 100% sure, but I think it's just on a large N effect. I think it would be a crossover, but the problem is that at large N you get really zero density here, and then this has to be second order. And so you see these two phase diagrams are really analogous in some sense, but again, this is only an analogy, and it would be nice to make it even more precise. So let's go to the last part of the talk. Let's include the interesting stuff. Let's include baryons and what we call the holographic realization of quarkyonic matter.
Nico, can I ask a question?
Yes.
Hola, Martín. You say that you include a term which generates the mass of the pion.
Yes.
But in the Sakai-Sugimoto model and these models with the flavor brains, you already had mesons.
Mesons, yes, but the pion was massless.
But you have a tower of pseudo-scalar mesons. And
there are a lot of higher modes of mesons that have a mass, but there is always one, which is the pion, which is the Nambu-Goto boson from the symmetry breaking that has zero mass. So in the original Sakai-Sugimoto model, the pion has exactly zero mass unless you do something else.
Okay, and the other thing is you heat up the model. Yep. Well, it's not at zero temperature, or
I'm looking at various temperatures. Yes.
So okay, but at some point you're going to have a competition between the mass of the Kaluza-Klein due to the compactification on the circle.
Yes, of course. That's why I said that I'm losing some top-down control of the model. I'm not including the possible Kaluza-Klein modes.
But you reach very soon this temperature. The temperature at which, the model reaches that very soon. Yeah.
That's possible. I don't remember now, but I am not including the Kaluza-Klein modes here. I must they're not in the game. Okay, so baryons. Let me be a bit quicker here. Baryons, we know that they are heavy objects at large N, and they can be introduced as solitonic d-branes, Instantonic d-branes wrapping an S4 in the geometry with NC strings that go from this D4 brane, this baryon D4 brane, to the flavor branes, which gives the baryon the baryon number it should have. The tension of these strings, however, pulls it towards the D8 branes, and within the paradigm of branes within branes from Douglas in '95, it can also be described as in terms of instantons of non-abelian gauge fields on the flavor branes. A strong coupling, however, the width of this instanton is very small, and for the purpose of this talk, I'm going to consider it just as a point-like source. But none of what I'm about to say, and we checked this explicitly and we did the computations, none of what I'm about to say depends on using point-like. It's just simpler and easier to see, but if you do it with the full-fledged instantons in some approximation, it works as well. So the important thing is that the baryons, when they appear in the model, when you go through the onset, they appear at the tip of the branes. And when they appear at the tip of the branes, they do so because it's energetically favored. But there have been several studies of different people suggesting that when you increase the density, they should move away from this tip of the brains, and they should go to higher values of the holographic direction. And so what we did is exactly that. We will, again, this was not really, this was suggestion only, and it was not implemented at the level of the solutions, neither at the level of the phase diagram. So what we'll do is we're going to allow the baryons to move away from the tip of these spherical brains. And what this is going to do is going to allow for baryons and these string sources I talked to you about before to exist at the same time. When we look at the full model, which is DBI action plus quark sources, plus baryon sources, and plus the mass deformation, if you want to put it in. And here the UC and UB, which are parameters which say at which point the cusp of the brains, the tip of the brains is, and at which point the location of the baryons, which are different or might be different. These are dynamical parameters, and when you solve the system, you find these 6 types of configurations. The 3 above are the ones I already showed you, and these 3 are configurations where you have, in this case, baryonic sources that have moved away from the tip, and then you have 2 types of solutions which have baryons and string-like sources or quark-like sources at the same time. And what happens if you look further at the way I'm not showing the details of the computations, but if you look at what happens, the baryons are really only affecting the physics above the point where they are located. The physics, for example, being the shape the D8 brains, the probe brains have. On the other hand, the quarks or strings, they are important in the lower region. And so what this gives is that it gives a holographic description, or we interpret it as a holographic description of the layer structure in momentum space I showed you at the beginning about quarkyonic configurations. And we're going to try to interpret these solutions as quarkyonic configurations from the holographic point of view. But there are 2 of them. One is like this, and it's roughly, if you don't have a mass, you can say that it's chiarly broken. And one is like this, and if you don't have a mass, you can say that it's chiarly restored. So it's a dynamical question, and you have to compare the free energies on whether quarkyonic matter in this context is going to be chiarly broken or restored. And what happens at 0 quark mass is that the only one that is really stable and that appears in the phase diagram is the lower one, so the chiarly restored one. So our interpretation of this is that, at least in the chiral limit, quarkyonic matter should be, or the transition to quarkyonic matter should coincide with the chiral restoration. And there are other types of things you can do here. You can actually, most of these results are numerical, but you can actually do the analytics. I mean, most of the stuff about the phase diagram is numerical, but you can do the analytics at 0 temperature, and it works. You can see that there's a continuous, again, even in this phase where you have these baryons here, there's a continuous transition if you increase the temperature, where these baryons melt and you go continuously to the quark-gluon plasma. And some properties of these phases are also similar to the quark phase. For example, the fact that the brains are straight, and other much more precise things that are in the paper, properties that are in the paper that are a bit in the spirit of the fact that whether these baryon or quark phases are really easy to distinguish between each other. And this is the phase diagram we get. And again, there are good things and bad things about this phase diagram. We show that the baryons staying at the tip are never favored as a solution. We show that the quarkyonic phase, the chiral restored quarkyonic phase, is important in the phase diagram. We show that there is a triple point here that appears in the right ballpark of QCD estimates. And that this transition here is first order and coincides with chiral restoration. The problem we have is that even though the baryons melt when you fix the chemical potential and increase the temperature, they don't really go away when you fix the temperature and increase the chemical potential. That's something you kind of expect because the Sakai-Sugimoto model has lambda, in this approach, has lambda fixed, and so you don't really have an asymptotic freedom in full-fledged, but again, that's one of the not so nice things about the results. And let me say that this is the phase diagram in the chiral limit, but this is very similar to what you get in when you include a very small pion mass or quark mass.
So even though it's a little bit piados to say something about finite n, is there some conjecture about how one over n corrections can change this feature, either in the good direction or the bad direction?
Well, there is actually, I have one interesting thing. I mean, I would like to make computations about that. I don't have much done, but I know that there is a paper which is very interesting, which obtains a solution which is, in some sense, very similar to this, although they never realized it was close to quarkyonic properties in any way, and they never said that in the paper, in the context of the VQCD models. So VQCD models is Veneziano limits, where you take NF and NC to be large, but you keep the ratio fixed. So you get solutions that are very similar to this in this model, and they seem to be there, and most of what I'm saying seems to apply. But again, it's only one other limit or approximation, and I'm not sure it holds everywhere, and I'm not sure about.
But it still is large n, right? So it still is large n.
It's still large n.
It's also
it includes the back reaction of the flavor brains, but it's still large n. Other than that, there are some hints from these people I showed before about lattice doing stuff and showing what changes if you go away from large n, but none of it is conclusive.
So your baryons are the usual ones in the Sakai-Sugimoto. They scale with n, with NC. They are the
yes.
D4 brains wrapped in the fourth sphere.
Mm-hmm.
Okay.
Okay, and so for the last, if I have 2 more minutes, I finish. For the last, let's look at the t equals 0 here. So here, if you start from 0 chemical potential and you start increasing densities, you go through the baryon onset, and then you go to the onset of quarkyonic matter, if you wish. So let's look a bit more precisely about what happens when you include a pion mass there. And at 0 temperature and 0 pion mass, what you have is like this. So this is the free energy, and remember that the system is always going to be in the phase that has lower free energy, and this is the baryon chemical potential. So at 0 temperature, what happens is you start from the vacuum, you go to the baryon phase, and then you go through a first order transition to the quarkyonic phase. But if you include the mass, this red line here has to disappear, because the straight brane solution is not a solution of the equation of motion anymore. And indeed it does, and if you include a small mass, this is what happens. So the blue, okay, sorry, and this is the quarkyonic solution with straight branes, and this is the other quarkyonic solution with string sources going outside of the horizon. And as you see here, the blue line is never the line with lower free energy, so it doesn't appear in the phase diagram at 0 mass. It's never stable. It's at most metastable. And what happens if you include the mass is that it's exactly this solution that at some point, instead of going to the origin, it goes back, it turns down. There's a turning point here, and it starts filling the role of the phase that has disappeared. And the interesting thing is that if you keep increasing the mass and pulling from this blue curve, you can actually, again, at masses that are higher than the physical pion mass, you can keep pulling from this blue curve, and you finally arrive at a continuous transition like this. So depending on the value of the mass and the way you're including it, you can really get a version or our closest version of the quark-hadron continuity, at least at high in the heavy regime, where you go from the vacuum to the baryon to the quarkyonic solution, and probably if you would have a better model with asymptotic freedom, you would go directly to the quark. already here in densities, but at least in our case, if at this point you heat up the system, you can go to the quark solutions where the baryons disappear. So that's what I wanted to tell you about. Let me summarize. What I have done is I have shown how to include the quark mass or the baryon mass in the Witten-Sakai-Sugimoto model at the level of the phase diagram. I have highlighted the importance of allowing for the baryons to move away from the tip of the brain, so to move in the holographic direction and not only to fill the spatial directions and 3 spatial directions. I have found what I think is a holographic realization of quarkyonic matter, at least in some sense. I have argued the relevance of this type of phases in the phase diagram and how it leads to chiral restoration at low temperatures. And I have described a concrete version of something like a quark-hadron continuity, at least in the heavy regime. And what I would like to do in the future and what I'm working on is, well, it would be, first of all, it would be very, very, very interesting to extend this to the confined geometry. So again, this was done all in the, assuming that I'm working in the geometry that has this black hole, but it's not at all trivial to understand how you can have this type of, if this is quarkyonic matter, it's not easy to understand how you can realize it in the confined geometry. But maybe you cannot realize it in the confined geometry if you are still at infinite n. I don't know. I really don't know. I would like to know the answer to that. And then there are more phenomenological points phenomenological directions I want to explore. One is to include the isospin as asymmetric matter, which is important if you want to describe neutron stars, because neutron stars are not neutron and proton stars. And also to include non-degenerate quark masses. I want to include more realistic baryons. Again, take the full instantons, which in some cases we did, but not all of them, with maybe crystals and non-homogeneous configurations, to include interactions, which we already know how to do in some cases, to include more layers. I want to study the applications of neutron star physics directly, and this is a very hot area of research right now, and there are various people really applying holographic things directly to compare with the observations about gravitational waves from neutron stars and not only gravitational waves. And as I was saying to Gaston, to include some effect of back reactions, NF over NC, or maybe 1 over NC, for example, understanding the difference with these PQCD models and so on. And that's it. Thank you for listening. And please, if you have any questions.
So, are there any further questions? Julian BA, you want to go ahead?
Thank you. Hi, Nico. Well,
Hi.
may I call you Nico?
Yeah, of course.
Okay. How do you control the temperature of your system, of your model?
Well, the temperature is part of the geometry. You have in the metric you have a blackening factor which has a parameter which is the temperature.
So it's given by the size of the black hole.
Yes.
So when you are at low temperatures, means you are considering small black holes.
Yes.
So
yeah, I know.
What happened with
very low temperatures, I agree that. I mean, again, I'm extrapolating in some sense. I tried to argue why it was interesting to do so, but I'm extrapolating. I know that at very low temperatures, the correct geometry is not that of the black hole; it's the confined geometry. In some sense, I'm trying to extrapolate because I think we found some interesting things, and it gives a nice way to construct a model which has, as I said, quarks, mesons, and baryons at the same time. But I really don't know how to. I'm not sure exactly how to extend this, all of this, to the confined geometry. There have been maybe 1 or 2 attempts to try to understand quarkyonic matter in this context, and none of them has been successful in any sense that I can think about.
Okay. And did you find any instabilities? If you have analyzed like perturbations?
Right. So that didn't get into the previous slide, but I mean, I've checked which phases are stable against each other within these configurations I showed, but I haven't done a systematic analysis of the perturbations. That's still on the to-do list. So I don't think I can say nothing more interesting about that.
Oh, thank you. It was a very nice talk.
Thanks.
Gaston?
Yeah. Okay.
Sorry. A quick question, Gaston?
Yeah, no, since you mentioned quark matter and neutron stars at the end,
Yeah.
since you have a holographic description, a proposal for holographic description, and you consider that this is for generic or at least a wide kind of class of quark matter, what do you? We know that there are several quark phases. One, for instance, quark-gluon plasma and going to a lower temperature, but still high temperature with big pressure. Now, the one that we suppose that are inside neutron stars or quark stars.
Yeah.
So,
yeah. Well, there are also several superconducting phases which I haven't included.
Yeah, in particular that one. So, what do you expect to see as such a phase transition in your dual model? I mean, you expect to find there what? I mean, from the dual.
That's part of the other answer. I really, I mean, there's no clear way to construct this in the confined geometry, which would be the transition you're kind of talking about, because if you don't have the horizon, I don't know how to make both type of sources coexist, because I mean, for me, the important thing are the string sources that go from I mean, you have the baryons and the strings that go from the branes to the horizon, and I can do that at very low temperatures if I have a black hole. But maybe I think maybe those string sources could reach something else. I mean, I've been thinking about, for example, having some type of baryon vertex that's outside of the branes, or that's fixed at some other point for some reason, and that in the sense that to have some other endpoint for the string sources to go to. I think that would be one way to try to think about it, but that's maybe as far as I can go. I mean, it's the most interesting question here, and I don't know the answer.
Okay, so